Welcome to the Wallace Project. My aims are to explore the possibilities of how life may evolve on alien planets, under conditions different from that of Earth. We will be looking closely at various levels of detail, at the cosmological scale, the planetary scale, and more closely at habitats and communities of life that have evolved uniquely to thrive in this exoplanet. This is the star system Wallace 22b. The large yellow star is called Wallace. It is a G-type yellow dwarf, main sequence star, similar in size to that of our Sun. The smaller red star is called Sarawak. It is a red dwarf star roughly 350 masses of Jupiter. The two stars are gravitationally bound to each other and rotate slowly, around a central point with a complete rotation taking several Earth years. This is actually quite slow for a binary star orbit, that can be as quick as 3 days. Let's take a closer look at the planetary system. There are a total of 7 planets. 4 of them orbit Wallace and only 1 planet orbits the dwarf star Sarawak. There is also a binary planet system that takes an elliptical orbit in a figure of 8 pattern around both stars. This pair of Earth-sized planets are named Zia and Ecco. For now we will focus our attention on these 2 planets, and we will take a look at the other planets later. The 3rd and 4th planets out from Wallace sit within the so-called Goldilocks zone. These planets receive enough energy for liquid water to be present to support the basic chemical reactions for life to develop. Life on alien worlds starts out when flood basalt lava, volcanic glass, is erupted from the sea floor and reacts with sea water to create RNA molecules, composed of random combinations of nucleotides. It is only a matter of time before an RNA molecule is generated that has the correct code of nucleotide bases to self-reproduce. Once this milestone is reached, abiogenesis has been achieved, that is, life from non-life. Here we have the twin planets of Ecco and Zia. They orbit each other around point in space halfway between the 2 bodies. A full rotation takes 35 Earth hours. Zia is mostly an arid planet with a few landlocked seas. The planet rotates once every 17.5 Earth hours. Ecco on the other hand a water world with a few small archipelagos. This planet has a slower rotation than that of Zia due to the effect of the ocean's tidal drag over its surface over the millennia. The tides on these 2 planets can be as high as 35 meters due to gravitational affect of its binary partner. Life on these worlds is complicated by these factors. For instance, when the tides come in on the land on Ecco, as much as 10 miles inland, may be covered with sea water, and then retreat again creating an enlarged strand biome. In addition to this difference from Earth, as mentioned before, the orbital path of the planets actually drifts out of the Goldilocks orbit for a month and then the planets closely orbit the red dwarf star, Sarawak, where they are bathed in dim dark red light in contrast to the white light of Wallace. We are currently in orbit around the planet Ecco. Shortly we begin our descent through the atmosphere. From orbit our sensors cannot detect any life signatures. The air is low in oxygen and very high in carbon dioxide and sulfur, indicating that there is not an established biosphere on this planet. The atmosphere is dense with water vapor and torrential rainstorms are fairly widespread. Volcanic activity is high similar to Earth during the Hadean period 4.52 billion years ago. After a bumpy ride through the atmosphere, our ship continues to submerge through the surface, into the depths of the deep ocean. The inky darkness is lit up by lava seeping to the surface. The seabed is almost entirely composed of slick black stone, basalt. We eventually find what we are looking for. Hydrothermal vents. These massive chimneys emit plumes of boiling hot mineral-rich water. We make detailed scans using the ship's sensors and discover RNA strings. RNA is the basic instructional information building block required for building proteins and is the precursor single helix version of DNA. On close examination, the chains of RNA are a scrambled code with only partial coded instructions for protein synthesis. Our ship is equipped with a time engine that will allow us to jump forward in time to see if the RNA molecules we found managed to evolve from its abiotic state into anything that resembles life. We are going to jump forward in time 3 billion years. This should give the upper crust and mantle of planet Ecco time to cool down. The hot oceans will help speed the chemical reactions required to create complex chemistry and biochemistry. I look forward to sharing what we find with you next time on Project Wallace.